it was this system. dx dt is x squared plus 2xy, and dy dt is, well, it was an A in the book because it was a one parameter family. Let's pick the A to be, well, let's pick it to be 1 to keep it simple. 1 minus 2xy minus y squared. That's our nonlinear system. And first thing to realize is when you look at a nonlinear system like this, in all likelihood, if it's sort of a randomly picked nonlinear system, it's not going to be a Hamiltonian system, and it's not going to be a gradient system. Hamiltonian systems and gradient systems are very, very special. Most systems are not. Random systems are not. But, you know, this is in section 5.3, which is about Hamiltonian systems. And so the idea is, okay, I guess this must be a Hamiltonian system. But how would you know that for sure? Call this function little f of xy and this function little g of xy initially. There's a test. What's the test based on? It's based on the fact that if this is a Hamiltonian system, then the right-hand side of the first equation is the partial derivative of the Hamiltonian function with respect to the second variable. And the right-hand side of the dy dt equation is the opposite of the partial derivative of the Hamiltonian function with respect to the first variable x. If this system will be a Hamiltonian system if and only if there is some function capital H where this is true. It also turns out that mixed second order partials for nice functions at least are equal. If H, which again is unknown here initially, is a nice function, meaning ordinary functions that you're used to, the second order partial of H, where we differentiate with respect to x first, then with respect to y, this notation you work right to left, this would mean differentiate with respect to x first, then with respect to y, equals the second order partial where you do it in the opposite order. And so the order really doesn't matter. This will be true for nice functions H. And therefore, coming back to the system of differential equations, if I differentiate f with respect to x, keeping in mind if the system is Hamiltonian, this will be a derivative with respect to y, it'll equal the opposite of the derivative of this one with respect to y. And that's the test, to quickly see whether the system is Hamiltonian or not. Take the partial derivative of f with respect to x. See what you get. Differentiate this with respect to x, treat y as a constant, you get 2x plus 2y. Does that equal the opposite of the derivative of the second right-hand side function with respect to y? What's the derivative of this with respect to y? Negative 2x minus 2y, then bring the minus sign through and you get the exact same thing. That's pretty rare for that to happen, right? Randomly chosen functions here, that's not going to happen. Very special thing there. These are equal. Therefore, the system is Hamiltonian. And then it's a matter of, okay, I'm going to find the Hamiltonian function, draw its level curves, and then the solution curves have to be on top of those level curves. The level curves become solution curves as long as you draw the arrows on top of them correctly. So you can do more than just ordinary phase plane kind of analysis. You can do more than just equilibrium points and linearization and null lines. You can use the level curves of the Hamiltonian function. How do you find the Hamiltonian function? Again, we did this last Friday, but we'll do it again. Since these functions are derivatives of the Hamiltonian function, to find the Hamiltonian function, I better integrate. This function is supposed to be the derivative of the Hamiltonian function with respect to y. So if I integrate it with respect to y, that should give me the Hamiltonian function. up to a quote unquote constant that could depend on x. It's not literally a constant. Integrate that with respect to y. Get x squared y plus, integrate this with respect to y. Think about it for a second, you'll get xy squared, right? If you integrate that with respect to y, treat the x as constant, you get a y squared, and you also divide by 2, which cancels the 2. Plus a constant that really is not a constant, it depends on x. I'm calling it phi of x because it's somewhat traditional, but again, this phi has nothing to do with flows. It's a constant with respect to y, if you pretend x is a constant. But hey, in the end, x is a variable, so I'm thinking of it as a function of x. I also want this to equal, the derivative of this, its opposite to equal the function g. So take the opposite of its derivative with respect to x. Differentiate this with respect to x, get 2xy plus y squared plus phi prime x. Distribute the minus sign through, negative 2xy minus y squared minus phi prime x. Look back up at the g function right there. Hey, it's looking good. You got a negative 2xy and a minus y squared, just like we have up there. We also have this 1. Okay, the 1 has got to be what negative phi prime of x is. Set this equal to 1 minus 2xy minus y squared. So negative phi prime of x is 1. So phi prime of x itself is negative 1. Integrate again to find phi of x. Get negative x plus c, and you really could call it a c now. But you can always take the c to be 0. We don't really care what c is. I mean, in a real-life physical problem, if H does represent total mechanical energy, potential plus kinetic, which it often does, then maybe the c does need to be something specific other than 0. But as far as drawing the phase plane, we don't care what c is. All the level curves, no matter what c is, will look the same. They'll give you different outputs for, you can have different Hamiltonian functions and you could get different outputs along those level curves, but we don't really care what the outputs are. We only care about the curves themselves. So we can take h, therefore h of xy can be taken to be x squared y plus xy squared minus x. In the lectures, I talk about special examples of Hamiltonian systems like the pendulum. Undamped, you don't want any friction for it to be truly Hamiltonian, for total mechanical energy to be conserved. Of course, in real life, total mechanical energy is not conserved because some of it gets dissipated into heat. But it's kind of nice to think about situations maybe where friction is small enough where the Hamiltonian system provides a good approximation, because it's just a nicer thing to think about, right? Friction makes things more complicated. And out in outer space, you know, friction is pretty small. Tiny bit of friction, I guess, from a molecule here and a molecule there hitting your spaceship. But all right, so now you'd want to use technology. So we'd want to plug this function into Mathematica. X squared times y plus x times y squared minus x. Making just a basic contour plot of this shows you its level curves. And adding more contours is typically a good idea. So you see more of them. Now, nothing about differential equations there. That's just a multivariable calculus graph. To relate it to differential equations, you need to draw arrows on top of these things. These things become solution curves for the Hamiltonian systems when the arrows are drawn in the right directions, which you can think about by thinking about null lines, the usual kind of stuff, sines of dx dt and dy dt. But if we're after seeing what it looks like as fast as possible, use stream plot for the given vector field, which was the system of differential equations, x squared plus 2x times y, comma 1 minus 2x times y minus y squared. Okay, and you can see those solution curves, which is what those are supposed to represent, do seem to lie on top of the level curves. There are two equilibrium points that I didn't make with big dots at 0, 1 and 0, -1, it looks like. You could double check that. If you take the vector field and plug in, for example, x equals 0 and y equals 1, you can do that like this. You get 0, 0, you get, it's an equilibrium point. The right-hand side functions are 0. I won't take the time to draw big dots. You could do that with list plot as usual. If you linearize near these points, you can see just looking at them, they look like they're saddle points, both of them. So in the Jacobian matrix, the determinant would be negative. In the trace determinant plane, you'd be below the trace axis, down where those points are saddle points. Officially speaking, that's the Hartman-Grobman theorem that justifies it. There are hyperbolic equilibria. The Hartman-Grobman theorem does apply. Are they stable or unstable? These two equilibrium points. Would you observe them? They're unstable, yeah. You only get stable equilibrium points for essentially sinks, spiral sinks, or centers. The kinds of equilibria you can actually observe in the lab. Other kinds of equilibria, saddles and sources, solutions don't approach them typically. I mean, yes, there are separatrices here that technically speaking mathematically do approach, for example, this equilibrium point right here, right along this null line here, approach it as t goes to infinity, but to have an initial condition in an experiment exactly on that that separatrix would be pretty much impossible. Because we're talking about infinite precision there as far as your initial conditions, and that would be pretty much impossible. In real life, you might get close to the equilibrium, but then you would go away. Most solutions in the long run head off to the right over here, to the left and upward over here, or downward this way. And the separatrices separate the plane into different behaviors of those solutions as t goes to infinity. Okay. Every Hamiltonian function for a Hamiltonian system could, if you want, also become a potential function for a gradient system. It's traditional to give it a different name, like V instead of H. H in honor of Hamilton, V in honor of nobody in particular. I don't know why they call it V. If I create a new system, dx dt, dy dt, where the right-hand side of the first equation is the partial of h with respect to x, not y. And the right-hand side of the dy dt equation is the partial of h with respect to y, not the negative, oops, typo there, not the negative of the partial with respect to x. So this is not a Hamiltonian system anymore. It's still the same right-hand side functions, they're just swapped. This one becomes x squared plus 2xy, right? Differentiate that with respect to y if you want to double check it. And this one becomes the opposite of the other one. The other one up here for the Hamiltonian was 1 minus 2xy minus y squared. Just negate everything. -1 plus 2xy plus y squared. It is the partial of this thing with respect to x. The level curves of h, you can call it v if you want, are the exact same that they were before because it's the same function. But solution curves of the system no longer lie on those level curves. They are orthogonal to them, right? That was a true-false question in the last exam. The system on the exam was gradient, so they don't lie on the level curves. If it was Hamiltonian, then they would. The null-clines are actually the exact same, except their roles get flipped. The x null-cline of this system, where f is 0, becomes the y null-cline of this system, where that's 0. And the y null-cline of this system becomes the x null-cline of this system. And the equilibrium points are the same. Will the equilibrium points change from saddle points to something else? Saddle points actually don't change. They still stay saddle points. So now I'm still going to make a contour plot of H, but I'm going to change the vector field here. Cut and paste here. And negate this one. So this now will be the gradient system. Still equilibrium points here and here at 0, 1 and 0, -1. And those equilibrium points are still saddle points, but those solution curves are very different. They're not lying on top of the level curves of the function. They are orthogonal to them. Every time they cross one of those, they're orthogonal to it. Gradient systems can come up with physical systems with friction. Probably more importantly, gradient vector fields are something that if you're in multivariable calculus, maybe you're starting to learn about line integrals, conservative vector fields. They are conservative. Line integrals are independent of path. They're probably more important for that kind of stuff. Okay, but you can think about them with differential equations too. Gradient systems also always have something called the Lyapunov function. And for a gradient system, the Lyapunov function is the opposite of the potential function. Give it a new name, call it L of xy in honor of Lyapunov, Russian mathematician Lyapunov. Usually, if we're calling the potential function v, we'd say it's -v of xy, but I didn't bother changing the name of the function here. Still calling it h. -h of xy is a Lyapunov function for this system. What does that mean? A function is a Lyapunov function for a system of differential equations if the rate of change of the proposed Lyapunov function along any solution curve is never positive. It's always less than or equal to 0. And in fact, the textbook, if you do the reading, emphasizes that it's only equal to 0 along a discrete set of points. If we differentiate with respect to time, L of what? L along a solution curve. Imagine x of t comma y of t is a solution curve. Now you have to use your imagination there because I don't know formulas for x of t and y of t. This is a nonlinear system. I'm sure formulas for x of t and y of t are impossible to find. They exist in an abstract sense by the existence and uniqueness theorem in chapter 2. But as far as, and we could approximate them with numerical methods like Euler's method, but as far as finding simple formulas for them, probably impossible. But knowing they exist, we can still think about what the derivative of this will be along a solution curve according to the multivariable calculus chain rule. You can think of L initially as depending on x and y, but then x and y both depend on t. You'll see diagrams like this sometimes. And the multivariable calculus chain rule in such a situation says to take a derivative like this, you got to find all possible derivatives along this diagram of L with respect to X, of L with respect to Y, of dx with respect to T, or X with respect to T, and Y with respect to T. Again, don't let the distinction between ordinary derivative notation and partial derivative notation bother you. It's just convenience. Just to remind yourself, in this case, that L depends on both X and Y. And then what you do is you multiply the derivatives along each path through this tree here, and then add the results. So we take the partial of L with respect to X. Oops, I put these in the wrong order, didn't I? That's an X there, and this is a Y. Take the partial of L with respect to X and multiply times the derivative of X with respect to T. Also take the partial of L with respect to Y and multiply it times dy dt, and then add the results. Hey, another linear algebra connection. That looks like a dot product, doesn't it? It is. Another linear algebra connection. That's a dot product of the gradient vector, whose components are these partial derivatives, and the velocity vector of the solution curve. I won't say any more. Anyway, if you find these derivatives, how? Well, with the partial derivatives, just use the formula for L, which is the opposite of this formula. So it's derivative with respect to X. Take the derivative of this with respect to X and then make a minus sign in each place. Well, it's going to be the opposite of this thing. What's dx dt? Dx dt is this thing. Let me pull its negative sign out as a -1. And the partial of L with respect to Y is the opposite of this thing. And the derivative of Y with respect to T by the differential equation is this thing. So what do we have here? We effectively have the negative of the sum of two squares. Negative of 1 minus 2xy plus y squared plus, in parentheses, x squared plus 2xy squared. And we're not dealing with any imaginary numbers here. This can never be positive. Wait a minute, where'd the t's go? How can these things not have any t's in them? T's are all in your head. They're there, I'm just not writing them. All these things do depend on t along a solution curve. I'm just not writing the t's, right? To keep it simpler looking. It wouldn't matter. All these things depend on t, but they still look like this. You still get a quantity that can't possibly be positive. Okay with that? Is this equal to 0 only at a discrete set of t's? Yes, but verifying that's hard and too hard for us, so we don't worry about it. What's the benefit of this? What's the benefit of knowing that's a Lyapunov function? In general, the benefit of having a Lyapunov function, which, by the way, does not, so this is going to be a Lyapunov function for a gradient system like this. And gradient systems always have the negative of the potential function as a Lyapunov function, but there are some non-gradient systems that still have Lyapunov functions. Say that again. Every gradient system has its negative potential function as a Lyapunov function. The derivative with respect to t along any solution curve can never be positive. But there are plenty of non-gradient systems that also have Lyapunov functions. So the idea of a Lyapunov function is more broad than gradient systems. But what's the benefit still? The benefit is that if you know there's a Lyapunov function, you can often use it to understand the phase plane better, prove things about it. It's especially useful in higher dimensions when you can't visualize things. Right? Once you get to higher than 3 dimensions, you can't visualize it anymore. But maybe if you're lucky, you might still be able to find the Lyapunov function, and that might allow you to figure out what's going on better. It's a tool. Knowing that you've got a function whose derivative along solution curves is always less than or equal to 0 is useful. Because, for example, if you draw level curves of this, effectively what this is meaning is that along the level curves of the Lyapunov function, solutions are going downhill. What do I mean by downhill? Well, that's kind of what's happening here. Oops, in the Mathematica. Okay, so again, these are the level curves for the potential function here. Can you see that number there? It says 0.64. This says 1.28, 1.92. Those are the outputs of the potential function, which is h. And they're getting higher along these solution curves. Solution curves are effectively going uphill for the potential function. So another important idea from multivariable calculus, gradient vectors point in the directions that the function increases, if you know about that. These solution curves are heading toward where h is higher in value, where this graph is lighter. That's a useful thing to know, to see that that's happening. And again, it could apply maybe in 4 or 5 or 6 dimensional problem where you can't literally visualize it. If we take the opposite of h, if we make a contour plot of negative h, it's a similar looking picture, but now the solutions are going downhill. They're going to where h gets smaller and smaller. Negative 1.28, negative 1.92, negative 2.56. And if I graph this function in a 3-dimensional picture, made a literal graph of the function as a surface in 3 dimensions, and if I drew the solution curves on top of that surface, they would literally be going downhill. That's what I mean. It's a visual thing. That's just a nice visual tool. Talking math here, pure math. I'm not thinking about the applications when I say they're going downhill. They're going downhill in a mathematical picture. That's a useful thing to think about. It's helpful for understanding. And again, possibly applying the ideas for higher dimensional problems. We try to do things in the easiest possible case, 1, 2, and maybe 3 dimensions, where things can be visualized. But you can apply these ideas to much higher dimensions and harder problems. It's not saying it's easy to apply it. Finding Lyapunov functions, well, for gradient systems is easy. Again, it's always the opposite of the potential function. That's easy. Finding Lyapunov functions for non-gradient systems is not an easy task in general. In fact, in one of the lectures, I do a harder example, and it's not easy. Harder example, it's not easy. Okay? But I think worthwhile if you want to try to see the big picture, maybe not trying to understand every single detail. All this stuff, by the way, if you took a graduate level stuff class on this stuff, it could be called like an advanced differential equations class. It also could be called like an advanced dynamical systems class, nonlinear systems. Those are the kinds of words you'd want to be looking for in such a class. And sometimes engineering grad school students do need to take such classes. Did I clarify anything? We're thinking about big picture ideas in the context of an example. I also, talk about trapping regions sometimes. Essentially, trapping regions, when you've got a Lyapunov function, are defined to be sets of points x, y, where your Lyapunov function is less than or equal to some constant. Once a solution curve gets in a trapping region, it's got to stay in there. Can't get out. That's why it's called a trapping region. And if your trapping regions in certain special problems happen to look like a ring shape, and you also happen to know there's no equilibrium points in there, There's a theorem I call the Poincare-Bendixson theorem that says there's going to be a periodic solution in there. Though you should keep in mind that's a special kind of application. Periodic solutions are pretty rare. You write down a random system, it's not going to have a periodic solution. But there's certain special systems where they do come up, and so it's nice to have that idea as well.